All right, hello. I guess I can start. Hello everyone, my name is Gorzny. I'm a technical lead and co-founder at Circuit, and today I'm going to talk to you about a methodology for replicating historical exploits on EVM-compatible blockchains, which is a bit of a mouthful as a title, but essentially it's going to be a way that we want to talk about how we can replay hacks. And why do we want to do that? Not so that we can pull them off again, but so that we can test various things. And if you know what we do at Circuit, you'll know why I care about this, and if you don't, you'll know in a few slides. So let's get into it. So first, I'll talk to you a little bit about the background, then some related work, and then we'll go into the challenges, what we are going to do, and what's left to do. This is not just work that I did myself. I am not that talented. I have a number of great co-authors, so if you see any of them, also feel free to ask them about this work. And you may have also seen this work at ICSI, a workshop at ICSI, which is a software engineering conference. But I wanted to bring it here because we all know that sometimes academics and practitioners don't talk to each other, and I don't think that's right. So here I am giving the talk again. Actually, it's my first time giving the talk, but the topic was given elsewhere. All right, so what do we need? What do we need, and why are we doing this? Why do we care? What's the background? So first, let's say there's a hack on the chain. What can we do about it? The first thing we can do is know about it. The first thing we want to know, is there a problem on chain with your dApp, with your system, whatever it is? You have to monitor the chain. There are solutions for doing this. There are a lot. Hypernative, Forta, Scam Sniffer. They all target different things typically. I mean, there's overlap, but Scam Sniffer maybe deals with phishing more than sort of exploits, and Hypernative maybe does the opposite. Maybe that's not true. I don't know, but there are certainly a number of vendors. Each of them will tell you what they do very well, or at least claim to do very well. And I've used some of these, and they are pretty good. By all means, check them out. I think monitoring is very, very helpful and valuable, but they only detect a hack going on, right? They typically, use analytics to figure out what's going on, to see, asymmetric value changes or something like this, and they operate passively to alert people maybe on Twitter, or to reach out to their clients or vendors if they have a connection to them, which is very helpful. It's better than nothing, by all means, and you can get a lot of information. You can then go investigate and try to do something about it. But if you have the notification that a hack is going on, it doesn't mean you can necessarily fix it. Some of the systems take it a step further, and it might include the list in the previous slide as well. I'm just spreading out the logos because I don't work for any of them and I don't owe them anything. But I do, want to, give everyone treatment. What you can also do is, if you know something's going on, you can try to block the hack. Right? So if you see a hack coming into your dApp, you maybe want to front run the exploit. Right? You want to say, okay, I'll steal my own funds, which is annoying, but I'll steal my own funds because then at least I can give it back later. Or maybe I can front run a pause on my smart contract so that no trades are possible. Or maybe I do something else. But this is something you either need to have pre-configured, or you need to be really, really quick at getting your signatures onto the chain in order to prevent, the hack from going through. So you have a very limited time frame, and even then, if there's a private mempool, or if there's some way you can skirt this, it's going to be very difficult. But you need to be active, you need to be timely, and when you have a decentralized team, maybe that's possible. Maybe you have someone around the world, or if it's automated, you can do it. That's a possibility. But if you are always, in Eastern time zone and the hack occurs at 3 in the morning, there's a good chance this approach won't work either. So we want to be able to look at both of these things and first monitor and block, if we can, in the situations where these are effective. But we need to know how to test these systems, and that will be the latest part of the talk. So if you're building a system like this, how do you be sure you caught what it is? And then there's one other step you can do in order to protect your applications, and that's build on Circuit. So Circuit takes it a step further, and I won't shill Circuit too hard here, but essentially, Circuit's a layer 2 network, a rollup, where we put an AI in the sequencer so that as transactions come onto the chain, we use an AI to detect them as malicious or benign. And so actually, if there's a hack on our network, the goal is to not include that hack. It'll be included in quarantine, and then we'll deal with it. And so you don't need to just be aware that it's existing, and you don't need to be panicking that you have to quickly pause your contract or front run the hack. Circuit will take care of that for you. So that's the goal. And why I'm interested in this research is because I want to make sure that I can convince you and anyone else in the room that Circuit's very effective at what it does. Right? I want to be able to say it would catch all the hacks in the past as well as multiple new hacks in the future. Right? Like, we don't want to just say we can do this and then hacks get through. That's not the goal. And so this work is a little bit of a hint as to how we tested our own methodology in order to ensure we don't have hacks on our network. Okay. So that's why we care. And if you do start looking at these, like I said, you need to know how you can trust them, and you got to figure out how you can test them. So there's a bunch of concerns you have. If you have only a monitoring tool, you have this passive detection. So how do you test that? Maybe it works, but maybe you don't know that it works under high TPS solutions or situations. Maybe the monitoring can't keep up. For example, if you're doing front running, it's not clear that you can always do this if you have private member pools, as I already mentioned. There's a bunch of challenges, right? And so there's actually a lack of testing methodologies. And I think this is sort of a false slide in the sense that the people building these systems almost certainly have these testing methodologies. They're not going out there and making outright lies about what they're doing. But from you as an external user, you want to be able to figure out what they're doing. And this work is also in that direction. So we wanted to come up with that and start thinking about how to do this. And by no means is it a complete effort, but we'll talk about that near the end. Okay, so what the problem actually comes down to, at least for the old hacks, is just making sure that at least the old stuff is caught, right? Security is a lot about growing and learning from the past. And while there are probably new hacks that are very difficult to figure out how they will work because no one's done them yet, we want to at least make sure all the stuff of the past is the stuff of the past. We don't want another reentrancy attack anywhere. Surprisingly, this stuff still happens. People still don't learn. They don't take the time. But we absolutely don't want, from the most interesting point of view, to replay the old stuff and have that hack go through because, that's the stuff we know how it should work. We should only be surprised by new stuff. And so what we want to do is we want to take existing hacks, use them as a testing data framework, and rejig them so that we can replay them anytime we want with whatever system we want on whatever network we want to make sure whatever we're doing to identify or prevent that hack works. And so what we're going to do is we're going to identify all the contracts involved. We're going to modify them so that we can put them on the network we care about. And then we want to replicate the system and the hack situation as best we can in order to test our own tooling. So what are people doing that aren't just those companies I talked about? And I'm sure there's more, by the way. But yeah. So what can we do? Well, there's a lot of small steps that you need to take in between none of this testing and a complete testing framework. So in particular, you have to identify a whole bunch of issues when you start to look at forking a smart contract that was involved in a hack. You need to figure out where was it executed, in what context. You need to figure out how addresses are handled. If you're taking a hack from Optimism, which occurred on Optimism, for example, and you want to replay it on a different chain, do they have the same token addresses for the things that were stolen? Does it matter if they do? What's the bridging address? Does it matter if that changes anywhere? Or what happens if you have cross-chain deployments? Or what's the purpose of the attack? There's a whole bunch of really small stuff. In the interest of time, I'm not going to cover all of these because I'd rather get to the bigger pain points. But the point is, there's a lot. In fact, there's even more. And we have a real problem here because this is a lot of work, right? To replay a hack exactly the way it is, and I will talk about this, I think, in a couple of slides, it's fairly straightforward. You can always sort of fork the Optimism chain at exactly the block the hack occurred on, if it occurred on Optimism, and you can replay exactly that transaction. You can see what would happen. But that is not the point of this work. In fact, we want to be able to take the hack and replay it in different situations, in different contexts, because that hack, exactly as it existed, already happened, and we don't care about it to some extent, right? We can't recover those funds or any, steps have been taken to overcome it already. But what we want to do is if we saw something similar, right? Hackers reuse ideas. Some of them are creative, others are very lazy. If we use similar ideas, can we catch it? Or if the hacker uses similar ideas. So you have to handle all of this. So all the stuff on the last slide, which I'll go back to, right? We have cross-chain stuff, purposes, address handling, all of that. Then what happens if you fork it? Did you fork it correctly and does it matter? What happens if you can actually replay or things like this? There's a whole bunch. I won't get into this. Please slow down the recording on the thing, take a look, or read the paper. We have this in a paper, so we can do that. All right. So all of that stuff aside, sorry, I'm going fairly fast. I do want time for questions. Why is this hard? Because actually it does sound like we have all the data. We have, the transactions are public unless it's on a private chain. It's another story. We won't talk about that. But we have, the hacker's address, the transactions that were involved. People look at this right away. And we have the smart contracts that were affected to some extent. Typically, the victims are always out in the clear because, you have DeFi protocols that people studied and want to know how they understand or how they work. And sometimes the hackers only give us the non-verified version on Etherscan because they're not trying to get themselves caught. But we still have some information. If we can do all of that, where can this go wrong anyway, sorry. Well, first, you have to replicate the exact situation for this hack. So you have to figure out what changes from the time that the hack occurred in the past that you're aware of to now when you want to do it on your current chain. And you might not want to deploy it on exactly the same chain. Obviously, I'm from Zircuit. I want to deploy all of these systems on some version of a local development of Zircuit so that I can see if my tooling will catch this. It does. But getting it to a context that is relevant for your tool's observation is very important, because you might be building this for a very specific client, right? You might go talk to a specific chain and say, I'm really interested in your chain because of reasons X, Y, Z, and I have this tool that's built for your chain. Then you have to also deal with address changes and contract configurations, right? Getting all of the same state so that the hack can be replicated is very, very important, and it's very hard. So let's take a look at a motivating example. So this is part of some hack, I believe. Maybe it's not. It doesn't even need to be. It's very simple, and even this provides us with several challenges without knowing anything about what's going on in terms of the actual offensive part of this hack. You have a contract, and you're just trying to redeploy it in a new context. And already we have at least 3 problems. First, you've hard-coded various addresses, which may not be the same on different chains. If you have tokens like WETH, it may exist on one chain at one address and another chain at another. So that's unfortunate. Then you also have dependencies. Almost all of DeFi has been marketed as money Legos, and that's for good reason. That composability is really cool and really interesting. But that means you have dependencies you need to also have in your testing environment. And then you also have things that go bad when you do things in the constructor, because maybe this is the hacker's contract and it can only be called by them, right? But you're not the hacker, or at least you're probably not the hacker, and so you need to change all of this. So already we haven't even got to the interesting part of a hack, and yet we have challenges to replay this. So this could just as easily be a software engineering talk. Okay, so we can tackle all of these, thankfully. Thankfully, these are somewhat easy. We have a constructor that needs to be sent by a specific person, we can change that. If we have addresses that need to be hard-coded, we can change that. We just got to go find out that information. That's out of scope of the work, so you have to do the mapping yourself, but it would be really nice if we could automate this and leave this as an open problem near the end. But anything else in terms of constraints, we can get rid of those, right? We can simplify this process. We're trying to replicate the intent of the attack, not necessarily the specific context, although that might not be always true, right? Sometimes you are looking at this code for hints, or you are using this stuff, but you can get around some of these. This will let you at least deploy the context for your hack, which is helpful. Then you got to go figure out all the changes on your smart contract addresses. So if you're attacking tokens or you're stealing tokens, they probably don't have the same one. I said this several times. You can change that too. That's not too big of a problem, which is very, very nice. But you also need to be able to change this in various ways. So if smart contract developers are getting more clever and they're doing things in different ways. So just make sure you catch all the places you do this. And then probably the hardest part, which this slide does not do justice, is to figure out, how do the contracts store the data? Even in, various implementations of ERC20 tokens, how addresses mapped and where things go changes. And so you have to be able to replicate this in any contract hack that you're also trying to replay. Again, the slide doesn't do it justice. Please see the paper for the more interesting parts of the challenges, but, you can also fix this if you're careful. And actually the way to do this is the methodology, which I think I'm getting to right now. Perfect. And so we can use a lot of this information to do it. And I'll go back to that example in just a second. But really what we're going to do is take the hackers' contracts and stuff that's, we already saw as the flow. They did a hack. We saw all that information. And what we're going to do is we're going to take all of that, modify the stuff that we need to surgically, and then replay the test and make sure our tooling works. And so in this case, we've got to identify exactly what's going on. Already went through the example, bunch of stuff that needs to change. And then we actually need to figure out anytime any of that's loaded into the EVM, for example, and we can start changing that, right? So actually, if you're doing it on a local version, if you're not trying to replay the hack on a public blockchain, which you probably wouldn't want to do because that would involve stealing real funds, but if you're doing this on your local version of it, you can go in and modify anytime any of these values load into memory and replace them surgically with the values that you need to make your replay of the hack happen, right? So if the hacker stole, 1 million of a certain token, maybe you only have a mock contract that has 10. I don't know if you're lazy like that. And you can change that anytime there's an S load. So that's basically where all the magic happens, which I don't have time to talk about in 20 minutes, let alone if I want questions. But getting into these S loads and figuring out where things are being changed is very important. And then you can also use proxies to get a little bit easier time with this. So what you can do is redeploy all of your hack contracts behind proxies so that you can sort of map token addresses a little bit more easily and address reads. Won't get into too much of it, but essentially, you can then upgrade and replay this and test as much as you want. And then finally, you configure all the storage as appropriate. If you don't want to do it in EVM, you can do it right on the smart contract level, and you redeploy the contract as appropriate there. So you just be surgical, you only set the context state that you need, then you execute your replay. And that's basically it. So that was very quick. I'm sorry, I'm pretty much on time though, so I will wrap up with some future work. And this is seemingly easy. What I said was just change the state to replay stuff, and that's a very, very easy blanket statement. But as always, the devil's in the details. And in this case, it's a several-page paper, so you have to go take a look if you want to learn more, or come talk to me. I do have time for questions right now. But it's not done. We're going to keep working on this. We want to do some of this, in the open, and we also want to share what we've been doing and validate this approach. So even, despite it being somewhat easy, air quotes, it's not perfect. Some things are very difficult to replay or replicate. So in particular, stuff that happens in real time or based on time values in your blocks, a little bit harder to do some of the surgical stuff. I imagine it's possible with a significant engineering lift, but it is going to be some work. And it's going to be difficult to replicate situations where you had a hack succeed or fail because of something like network congestion. If you had a lot of transactions and somehow the exploit uses that, I don't know exactly how, that might be very challenging. It's not just about surgical state changes, it's about replicating all of that as well, and the methodology doesn't do this. Nonetheless, we started doing this by looking at the damn vulnerable DeFi hacks repository and starting to see if, can we at least do the simple part of doing this state change to replicate the hacks and detect them. We did detect them, it does work, and we were able to validate this approach, which means if you are interested in testing your tooling on hacks, starting there and using this code, which I don't know if it's open source, so come ask me about that, is a valid approach and one that you can actually succeed with. Ideally, what we'd really love to do is replicate this in an automatic fashion. So if we see a hack occur, build some tooling around changing the surgical state to identify, which parts of the state need to change to replay it. That is going to be ongoing work, and we're going to be happy to talk about that in the future. But at least for now, we can manually go back and say, at least on Zircuit, and with the tools that we tested, the hacks that we saw in the past won't be hacks again on our network or anyone using those tools to prevent those systems, which I think is a good step forward. So, thank you, and I think I have time for questions. Yeah.
If you have a question, please raise your hand. Okay, I see.
Thank you. I'm curious, for security practices for engineering teams, what external tools would you recommend, like Slither or Aderant, for them to, during their development lifecycle, kind of be checking proactively to prevent potential?
Okay, I would love to give you a really, really good answer, and it's been a while since I have personally used the smart contract code tooling. Slither was always one of the ones that worked really, really well, and I don't have any other recommendations at this time. A lot of people will tell you to use an LLM. I will say be very cautious. I think there's a good place to start, or they're good tools to augment, but I don't have full confidence in just shoving it into like ChatGPT. So I will just give you that anti-recommendation and say, come find me, or I can recommend you to auditors who can definitely tell you better tooling.
Thank you for the question. Any more questions? Yeah.
So you're changing a lot of you're not replicating the exact construction process of the contract, obviously, for this. Do you see a lot of hacks that occur like during constructor code? Because this would imply that that wouldn't work for this. So I'm just wondering.
Yeah, I think you can also be more surgical on what you comment out, right? So I think of the motivating example, we just killed the whole constructor there. But if it's just the requirement that the sender needs to be the attacker, you can change that and be more surgical. Ultimately, those types of requirements also need to change, not in the constructor as well, right? If sure. The hacker calls a function, which also needs to be gated by their address, that also needs to change. So it's not just a question of, is the hack going to occur in a constructor? It's going to be, can we surgically do these changes to the attacker's contract that lets us replay it from our point of view? And so I think it's yes, we can, because you could, as an attacker, probably also move most stuff to the contract or to the constructor, right? So it's sort of like a meaningless distinction of if the hack occurs in the constructor versus not, except maybe one extra level of transaction call from the attacker.
Do you see that most of the hacks that you see are they not in the constructor code? I would.
So okay, yeah, then that's the perfect follow-up, and I don't have the answer for that. I would have to ask my co-author who took a look at it. There's actually a good chance a lot of it will be in the constructor, because then they deploy and execute at the same time. And so if a system had static analysis tooling to detect old contracts deployed, it wouldn't be able to catch something like that.
And where can we find the link to the paper?
That's a good question. I will tweet it after, and I will, share it.
Thank you for the question.
I should have put that on the slides.
Yeah, thank you to the speaker. And
Great. Thank you.